Welcome to the Mechanics of Materials lab. Today we are going to demonstrate the combined loading experiment. Now the way we call it as combined loading, because when you have multiple loads acting all together in a sample or in a real structure, in that case we can call this as a combined loading setup. In terms of the lab experiments, we have a setup like this. Let me explain what we have. Here we have a cylindrical tube. Okay, so we might know its inner and outer diameter and the thickness of the tube. And with this tube, at the very end, you can see we have a rectangular beam that is connected, and these are very perpendicular to each other. And the way we're going to set it up, we're going to fix this left side. Okay, so this end will be fixed, and we'll try to put some load at the very end of this beam. So when the beam is experiencing the load, this beam is under bending, and due to this bending, this tube would experience the torque. So we have a torsion in the tube and a bending on the beam. So this is where we have two different kinds of load, so two different kinds of stresses are acting together, and we are calling it as a combined loading setup. So the way we do this experiment, we first try to find out the change in strength with different loads, and then convert from strain to stress, and use some sort of Moore circles and 3D Hooke's law. You should get that in your lab handout. Now to get the strain, let me show you what we have here. We have some strain gauge on the very top surface of the tube. Okay, here you can see I have three strain gauges. Now this combination of gauges, we call it as the rosette. So this is a strain gauge rosette. We have three gauge. The very right side I have a gauge, we would call it as a 0 degree gauge. In the middle, which is aligned with this tube, we can call it this as the 45 degree gauge, and the other one is the 90 degree gauge. So we have three gauge, 0, in the middle I have 45, and on the left side I have a 90 degree gauge. And we will try to connect this three gauge in terms of a three-wire bridge, quarter bridge circuit, and from there we will get the strength. So let me set it up, and then we can show you how to connect it in the gauge, strain gauge indicator, and how to get the readings. So to fix the fixed end, you can use some sort of fixtures like this. Okay. So quickly, I'm gonna fix the setup. Let's put another one on the left side. Okay, so we have a fixed end, and let's connect these strain gauges now. Now to get the strain readings, as you have already seen from the Poisson's ratio experiments, we're going to use the strain indicator. If you turn on the power, you can see there are 4 channels, channel 1, 2, 3, 4, and we have 3 gauge, so we need to use 3 channels. Okay, and let's start with the first one. In terms of the circuits, as we said, you should connect it as a three-wire bridge, a three-wire quarter bridge connection. You can get these circuit connections from this this window. Okay, so we're going to use the first one. You can see the connections. We have where there is going to P plus, and then we have a common end. One end is going to S minus, and the third that is going to D. So it's a 120 ohm strain gauge, so we'll be using the first D 120. So P plus, S minus, and D 120 are the channels. Now the way the gauge is connected, our red wire, okay, the red wire, this one is going to be connected with one end of the gauge, which goes to the P positive, and black and white, these two are going to either S minus and D120. So let's connect it accordingly. So I'm going to use channel number 1 for the first one, 0 degree gauge, channel 2 for 45, and channel 3 for 90. Okay, let's take the second one. We will do the same sort of connections. 0, and black goes to 45, and white, that is going to 90. Okay. Third channel, red goes to P positive, black, which is going to my S minus, and white is the D, that is going to the D120. Okay, if you do not see any reading there might be some misconnection. Okay, so we have our connections done, and you can see 3 strain readings since we have connected 3 channels. The next thing would be check what type of bridge is there. We need to connect it in terms of the quarter bridge. Okay, so let's hit the bridge. So we can get here channel 1, 2, 3, all these 3 are quarter bridge, so the bridge is okay. If not, you can go back and forth and check your bridge type. Okay, once you are satisfied with the type of bridge, you can hit the menu to come out. The next, check the gauge factor. So the type of gauge factor we have to use, it depends on the strain gauge, or in this case rosette, and this should be provided by the manufacturer, and we have the information in our lab handout. You can get the gauge factor from the lab handout. Let's hit this K. So the type of strain gauge we're using, a rosette, our gauge factor should be 2.02. So check whether you have it. If not, you have to change it to the accordingly 2.02. So we have right now channel number 1, it's showing the strains in terms of microstrain and gauge factor 2.02. So this is okay. Let's check the second one. Same thing, microstrain and gauge factor 2.02. This is still fine. The third channel, channel number 3, unit microstrain and gauge factor 2.02. So all 3 strain gauge are with the correct bridge type and in the correct gauge factor. Once you're satisfied, hit the menu. Now we need to balance the gauges. Okay, so you can hit the balance. Just hit the balance. Now what it is trying to do, it is trying to balance all these 3 gauges, 0 degree, 45 degree and 90 degree gauge. Once this step is done, I can hit record. So right now we have pretty much 0 strains in all the 3 readings. We have the correct gauge factor, we have the correct gauge type, and we don't have any preload here. Now one thing we can do to put the loads, we can hang this hanger. Okay, and we're getting some sort of microstrain. So what we can do, let's balance the gauge again so that we can start from 0 pounds, 0 load, 0 strain. So I'm gonna repeat the process again. Hit balance, balance again, and record. So what we're trying to do here, we're neglecting the little bit of effect of this wet panel. Okay, so right now we're at 0 pounds, and the lab handout says we have to increase the load from 0 to 2 pound, 4, 6 until maximum 10 pounds. Okay, and for each case we want to record what are the strains in our 0, 45 and 90 degree gauges. Then use those strains, convert into stresses, and use the Moore circle, use the Hooke's law. All these steps should be there in the lab handout. So a few things we want to check here. We want to check whether the relation between the load and strain is linear or not, and our theoretical stress calculations and experimental stress calculations, how perfectly we can match it. Okay, so all these loads are of 2 pounds. Okay, so let's put the 2 pound load and get the strengths. So for 2 pound we're having 100 microstrain for the first one, 123 microstrain for the 45 degree gauge, and -9 microstrain for the 90 degree gauge. Okay, now what we're going to do, we're going to increase the load and go maximum 10 pounds. So your job would be to record the strains for each load state. Okay, let me go ahead and put the maximum 10 pound and see what we get. Okay, so right now I'm putting 6 pounds. So for each case, remember we have to record the strains, check the linearity. This is 8 pound, and finally I have here, this is just 10 pounds. Okay, so that is the maximum load we are putting into our combined loading setup. So for 10 pounds applied load, we have a bending on the beam and a torque on the tube. So we have a stress due to the bending, we have a stress due to the torque. You take care of both these two to find the combined effect. Okay, so just let me read out the data. What we have here, we have for 0 degree 482 microstrain, 45 degree 617 microstrain, and for 90 degree this is negative 46 microstrain. Use this data for all the subsequent calculations. Once this step is done, you take all the loads back and come back to 0. So all the strains should also come back because of the linearity, and we are in the elastic limit. So I'm taking the load back, all the strains should also come back. Alright, so let's quickly show you what is we're getting at when we unload the sample. We're getting -6, -5, and -3. So this is pretty much 0 where we started. So all the loads have been taken back, so all the strains is also taken back, and we are in a perfectly linear zone. Alright, so once you have the strain data, the next is the calculations, and you can follow the handout for the subsequent calculations.